Hi, welcome to my channel, JaberTime. We're going to talk about rational functions. As you can see, I have three different graphs. They cover vertical asymptotes, horizontal asymptotes, slant asymptote, removable discontinuity, or what's called holes in the graph. Let's get into it. Rational functions. This is the formal definition. A rational function is a function that can be written as the quotient of two polynomials p of x and q of x. P of x and q of x. Of course, we don't want the denominator to be 0. That's stated right here. The leading term right here is a sub p times x to the power p, which leads us to the degree of the numerator. And the leading term right here is b sub q times x to the power q, which gives us the q as the order of the denominator polynomial. Because these leading terms and the leading coefficients, they do mainly affect our discussion in this section. The domain of rational functions includes all real numbers except those that cause the denominator to be 0. Anything you could plug in is fine, except what makes the denominator equal to 0. We should take it out of our set of domain. Here's a quick basic or parent function 1 over x. As x approaches 0 from the right, when you come this way, you're taking off, you're going up to infinity. Why is that? Well, once you go and plug in 4, that's 1/4, then 1/3, then 1/2. As you can see, 1/2 is greater than 1/4. Then 1 over 1, which is 1. If you plug in half, 1 over half is like 1 times 2 over 1. When you change division to multiplication, you flip the fraction, which is 2. So at half, take a look at the graph. At half, you are up to 2. Imagine if you plug in 0.1. Well, 0.1 is 1/10. And 1 over x means the reciprocal. So 1/10 becomes 10, as you could see. All right. Even smaller, look at 10,000. So as you get close to 0 from the right, and that's how we read this, you are going up to infinity. Positive stays positive. If you approach 0 from the left, this is not -0, of course. Approaching 0 from the left, you're going to go down. With the same concept, same idea, but with negatives. At the end, we call it end behavior model. As x approaches infinity, when a fraction like this one and the denominator gets bigger and bigger, the value of the fraction gets smaller and smaller. So if it's positive values, it's going to stay positive, small numbers. So you approach 0 output from the positive side. Same thing right here in behavior. If you plug in -1,000, that's 1 over -1,000, which is a very tiny, small amount in negative. So you're approaching 0 from the bottom side, you're always staying negative. Here's more detail about 1 over x and 1 over x to the second. If you move from 1 over x to 1 over x to the second, what happens? No more negatives. That's going to be positive up here. It's going to be reflected about the x-axis. Not only that, look, it's getting closer here compared to this, right? Because that's going to be smaller, faster than this. 1 over 10, 1 over 10 to the second, that's 1 over 10, 1 over 100. So when you plug in 10, you get 1/10. When you plug in 10 here, you get 100s. You get smaller. And this is going to be flipped, reciprocal, faster than this. So anyway, The idea is it's almost the same, except instead of being down here, you're going to be reflected above the x-axis. This says in behavior, as x approaches infinity, f of x approaches 0. In behavior, as x approaches negative infinity, f of x approaches 0. And we did talk about this in the previous graph. That's approaching 0 from the right and approaching 0 from the left. Now, why we have these graphs? Because we're going to talk about horizontal and vertical asymptotes. This right here will be called horizontal asymptote. You get close to it and you don't cross, or you don't touch. Here, it's vertical asymptote to the graph. This one here has a vertical asymptote also, y-axis, horizontal asymptote because it's not gonna touch it, at least for now, the way we understand. We don't want to talk about other ones that will be called horizontal asymptotes and goes through it, but let's just stay focused on this one. So both, they have horizontal asymptotes as x-axis and vertical asymptote as y-axis. Same concept, the original graph and a new one. Looking at the vertical asymptote, a vertical asymptote of a graph is a vertical line x equals a, in this case x equals 0, right there, where the graph tends toward positive or negative infinity. The graph tends to positive or negative infinity as the inputs approaches a, which is 0. In this case, as x approaches negative 2, that's my negative 2, from right or left, my values, my outputs approaches infinity on the side, negative infinity on the side. So you get closer to it and you just keep going with it. That's what this one is describing. So we have a vertical asymptote at x equals negative 2. We have a vertical asymptote at x equals 0. As x approaches a, f of x goes to infinity, or as x approaches a, f of x goes to negative infinity. Looking at the horizontal asymptotes, this is a horizontal asymptote which is called y equals 0. This is a horizontal asymptote which is called y equals 3, the dashed green line. A horizontal asymptote of a graph is a horizontal line like y equals b, in this case y equals 3, where the graph approaches the line, as the inputs increase or decrease without bound. As x approaches infinity, as x approaches negative infinity, approaches the line. The graph approaches the line, gets closer to the line. We write as x goes to infinity, or as x goes to negative infinity, going all the way right, going all the way left, your outputs are getting close to, in this case, 3. Same thing applies right here. Now I have the equation right here in two different formats. This graph compared to this graph, it's like shifting it to the left 2 units and 3 units up. 2 units to the left, 3 units up. If you write this using common denominator, it looks like this. We're going to discuss in this video more concepts, but while I'm here, I'm going to spend a few seconds and talk about it. This is linear, same degree. Looking at the leading terms, 3x and 1x, the leading coefficients 3 over 1, that's your horizontal asymptote, 3. If you don't understand it yet, I'm going to go over it in detail with more examples. But while we are here, I just want to let you know that the horizontal asymptotes comes from rational equations or functions that they have the same degree, top and bottom, numerator, denominator, and you take it from the leading coefficients ratio. The vertical asymptote is at x equals negative 2, which is the 0 of the denominator. The denominator will equal to 0 at x equals negative 2. Something useful to look at. Let's see more examples. We did talk about this in detail. Something to keep in mind. Vertical asymptote, horizontal asymptote. This one right here, horizontal asymptote at y equals 3, vertical asymptote at x equals -2. And I did talk about looking at the fraction or the rational function. Here's one more comment. As x goes to infinity, this will go to 0, right? What do you think? As x goes to infinity, this will go to 0. That will stay with you. So it's almost like it's going to be 0 plus 3, which is 3. You are approaching 3. That's just like another comment. Okay, moving on. That's the same problem, but in more detail. Using transformations to graph a rational function, sketch a graph of the reciprocal function 1 over x. That's right here. That's the reciprocal function. Shift it 2 units to the left and up 3 units. Identify the horizontal and vertical asymptotes of the graph, if any. We just talked about this, but in more detail. By shifting it to the left, we're going to subtract or add 2 to x. By shifting it up, we're going to add 3 outside. By using common denominator, you could write it as a fraction. Now pay attention to the leading coefficients, which I mentioned earlier, and look at the degree. I kind of mentioned order first. The degree of the polynomial on top and the degree of the polynomial at the bottom side. They have the same degree. You take it from the leading coefficients, which is 3 and 1, and that will be your horizontal asymptote. That's the y equals 3. That should do it for this problem. I think I said enough about this. Let's move on. Removable discontinuities of rational functions. This might be new to you. Removable. A removable discontinuity occurs in the graph of a rational function at x equals a. If a is a 0 for a factor in the denominator that is a common factor with a factor in the numerator. What does that mean? We're gonna read the notes and I'll show you some examples quick. We factor the numerator and the denominator, and we look for the common factors. Then we find the zeros for those common factors. This is the location of the removable discontinuity. It's more clear when you see it in examples. This is kind of still dry. I'll show you some examples in just like less than a minute. This is true if the multiplicity of this factor is greater than or equal to that in the denominator. If the multiplicity of this factor is greater in the denominator, then there is still an asymptote at that value. It's kind of hard to talk back and forth about these notes, but I want to have it in the video just in case if you want to go back and double check the notes, and instead of looking, let's say, outside for more details about this. This covers it all. But let's get into it and be practical and look at some examples, which is going to describe most of these ideas. Here we go. Find the domain of this rational function. Most of these problems that I have, I could talk about it from all different angles, but in some cases I will stay focused on the keyword for that problem. You'll see in just a minute what I'm talking about. The domain of this function. We begin by setting the denominator equal to 0. X to the second minus 9, because that's what the problem comes from, the denominator. Once you make it equal to 0, you could move the 9 to the other side take the square root of both sides, and I get x equals plus minus 3. Or you could just factor it as difference between two squares, and you get plus minus 3. The denominator is equal to 0 when x equals 3 or when x equals negative 3. So the domain of the function is all real numbers except at x equals 3 or negative 3. Differently, we could write the domain this way. From negative infinity to negative 3, not including negative 3, union from negative 3 to 3, union from 3 to infinity. Now, we're done with this problem because it says domain. But why not go further than this and add more to it? Because this is a lecture video. It's not just like solving an example or two. Let's add more to it. Look at this right here. If you factor the denominator and keep the numerator in your way, I'm using green for x plus 3, as you could see. Now this factor cancels if x does not equal to negative 3. Because you can't divide by this and this if it's 0, right? So here's the denominator. It gives me two zeros. But the green one is repeated up. And that's what the previous page was talking about. To make the story short, the one that doesn't cancel, which is in blue, gives you x equals 3. You have a vertical asymptote. The one that looks like in the green, which leads you to x equals negative 3. X equals negative 3. That's a 3, and that's a negative 3. At negative 3, there is a hole in the graph. There is a vertical asymptote at x equals 3. There is a hole in the graph at x equals negative 3. I'm keeping the blue with the blue and the green with the green. That's a hole in the graph, and that's a vertical asymptote. So we have a removable discontinuity at x equals negative 3. Here's the graph. It's a little bit small to see it, but take a look. You see the hole right here? There is a hole in the graph at x equals negative 3. And there's a vertical asymptote at x equals 3. Vertical asymptote at x equals 3 coming from here. And at x equals negative 3 coming from here, there is a hole. Why they call it removable? Because I could redefine this function and call g of x equals this when x does not equal to negative 3. And on the second line as piecewise defined function, I could fill it in and make it continuous. Like, you know, the piecewise defined functions, we could, whatever the value is, plug it in and make it filled as continuous. That's why it's called removable, because it could be fixed. This is not fixable. We can't twist them and make it connected. We can't. So it doesn't hurt, as I say, like to talk about only the domain and stop right there to see this in detail. Green and blue. Another function, quick. I'm not writing any title, it's more for discussion. Factoring it with colors. Top and bottom side. See the green? Looking at the denominator. Setting the denominator equal to 0. I have the zeros. Now what do we say to close this problem? I'm not writing much here because we know some, or we know enough to see it clearly with colors. At x equals negative 1, the green one tells me x equals negative 1 as a 0. We have a removable, there's a typo right here, discontinuity, which is a hole in the graph. At x equals 3, we have a vertical asymptote. That is clear. All right. That's what we care about, the zeros of the denominator, the ones that cancel with the numerator. It's called removable, or describes the graph as a hole in the graph. Vertical asymptote, hole in the graph. One more example. Let's factor it. We have a 0 here at 2. We have a 0 here at -2. We set the denominator equal to 0. So if we need the domain, we say the domain is all real numbers except 2 and -2. But let's describe the vertical asymptote and the hole. At x equals 2, I'm looking at the green. It's a hole in the graph. At x equals -2, it's a vertical asymptote. And here's the graph to support. At 2, it's a hole in the graph. At -2, it's a vertical asymptote. Now, talking about horizontal asymptotes from different angles in detail, here's some notes. Identifying horizontal asymptotes of rational functions. The horizontal asymptote of a rational function can be determined by looking at the degrees of the numerator and the denominator. So we talk about the degree of both p and q. P for the numerator and q for the denominator. We have three cases. The degree of the numerator is less than the degree of the denominator. In this case, we have a horizontal asymptote at y equals 0. I'm going over this a little bit quick because I have two examples for each one of them coming right after this slide. The degree of the numerator is greater than. So once it's less than, horizontal asymptote. Once greater than, no horizontal asymptote. You have a slant asymptote. And here it says greater than of the denominator by 1. So which makes a difference. All right. 1 is something highlighted or clearly stated right here. The degree of the numerator is equal to. So less than, greater than, equal to. When it's equal to, we have a horizontal asymptote at ratio of leading coefficients. We saw that earlier, but let's just focus on details about each one of them. Let's take the green one first. When the degree of the numerator is less than the degree of the denominator, we have a horizontal asymptote at y equals 0. Degree of the numerator is less than the degree of the denominator. We'll think about it before we move on. This is what the note says. The degree of p of x is 2 less than the degree of q of x, which is 3. So there is a horizontal asymptote at y equals 0. Now, I don't have to memorize this. To me, it's a common sense. Let me show you why. As you plug in 1,000 and a 10,000 and a million and a billion, this is a second degree. This is a third degree. This is going to take off. It's going to grow so fast compared to this. And that's why the value for the whole fraction goes down to 0. Think about it. A billion times a billion times a billion compared to a billion times a billion. Even higher. So eventually, this is going to grow faster, way faster than this. And the whole fraction will tend to be 0. Closer and closer to 0. And that's why we are getting closer and closer to 0. Let's take another example of the same topic. Degree first, degree second. With that in mind, those are the main terms, the leading terms that affect the end behavior. Sometimes we describe it by g of x. Your f of x becomes almost another function which is g of x, if you want to call it. So that's another function towards infinity. If you want to simplify this, it's like 4 over x. If this grows up, the whole thing goes to 0. So you have a horizontal asymptote at y equals 0. Alright? I think that is clear. Less than, you're going down to the x-axis. If you're above, of course. This one right here, if you factor it, 5 times 1, and you need the 5 to be positive, so it gives you a -5 when you find the zeros. You have vertical asymptote at -5 and vertical asymptote at 1, but graphically you are getting close to y equals 0. So you do have a horizontal asymptote as you approach infinity, even though you cross it right here. But this behavior is described as horizontal asymptote from both ends. Alright? Let's move to the second case. The second case where it says the numerator is greater than the denominator. Think about the common sense one more time. The numerator is bigger. The top part is bigger. What does it say here? No horizontal asymptote. Of course, because you're going to take off. But if it's greater by 1, you're going to have a slant asymptote, which is something might be new to you. We don't see it in lower math like algebra 1, but it's right here, and I'll show you. Degree 2, degree 1, that's one more. 7th, 6th, and so on. That's the case. Take a look. There is a reason for by 1 more. The degree is 2, the degree is 1. Since 2 is greater than 1 by 1, as they say by 1, there is a slant asymptote at y equals x minus 2. Where is that coming from? Let me show you. If you attempt to do a long division or synthetic division, dividing this x plus 2 into this, x into x to the second is x, then the x times x, and x times 2, I get x to the second plus 2x. Change the signs, cancels. I have minus 6x. Bring the 1 down. Negative 6x into x will give me negative 6. Multiply, multiply. I get minus 6x minus 12. Change the signs and add. This cancels, and I have 13. So what this means, it means the following. That your fraction or rational function is the quotient x minus 6 and the remainder 13 out of x plus 2. Yes, x plus 2. So towards infinity, what happens here? This will go to 0. This is what will stay with you. And that is called slant asymptote. So back to this, why they say greater than the degree here is greater than the degree here by 1, because when you divide a 7th degree by 6th degree, for example, you get a 1st degree. Because if you go back, 1st times 6th degree will take you to 7th degree. That's the idea. So your quotient will be linear as a straight line. So you're approaching a straight line. The second example, I have a graph for you to show you more detail. Here's another example. 3x to the second minus 2x plus 1 over x minus 1. If you divide long division, we get 3x plus 1 plus 2 over x minus 1. Towards infinity, this will go away, will go to 0. In other words, this will stay with you. So you're approaching a line. You're getting close to b with this guy, which is 3x plus 1. The slant asymptote is the line y equals 3x plus 1. 3x plus 1 is the green line. You're going to get close to it because that's going to go to 0. And if you wonder why the vertical red line is there, it's a vertical asymptote at x equals 1. It's right here, from here. So it all adds up, as you could see. I have enough ideas. It's kind of hard to talk about all the ideas in one problem, so we saw different graphs and different examples. Let's see. I think I have one or two more for you. No, actually, I have the third case. I almost forgot about the third case. Here's the third case. Degree of the numerator is equal to third degree, third degree. Two examples for this case also. In case they are equal, we talk about the horizontal asymptote at the ratio of the leading coefficients. The leading coefficient is 6x to the third. The leading coefficient is 2x to the third. The ratios of the leading coefficients, that's 6 over 2, which is 3. Here we go. The degree of p of x is 3. The degree of q of x is also 3. And they are equal. So we can find the horizontal asymptote by taking the ratio of the leading terms 6x cubed and 2x cubed. Differently, we're looking at 6 over 2, which is 3. Which makes sense. Towards infinity, those are not going to count much. So it's almost like you're staying with these, which simplifies to 3. Last example. The degree of the numerator is equal to the degree of the denominator. Yes, we do that. We have it. Looking at the denominator, which is called q of x, I'm starting with minus, setting it equal to 0. We don't like the minuses, so we could get rid of the minus by multiplying by a negative. Now I have x squared plus x minus 2 equals 0. Factor it, I get two zeros, 1 and negative 2. So we have vertical asymptotes because the top part does not give me a factor to cancel these. Remember the color green that I used for a whole or removable discontinuity? I don't have it here. So I have vertical asymptotes at x equals 1 and x equals negative 2. All right. The degree of p of x is 2 and the degree of q of x is also 2. So we have a horizontal asymptote at the leading coefficients 2 over negative 1, because towards infinity that's what counts, the leading terms, and that will simplify to the ratio of the leading coefficients, which is negative 2. Here's a graph to support. We have vertical asymptotes at 1 and negative 2, at 1 and at negative 2. And we have a horizontal asymptote at the leading coefficients ratio, which is y equals negative 2. That should do it. It's about half an hour or 32 minutes. That's my plan, and my goal is about 30 minutes as lecture videos with enough examples. Thank you for watching, and I'll see you in the next one. Thank you. Thank you for watching. Don't forget to hit the like button, subscribe to see some more, and I'll see you in the next one.